In today's lecture, we are going to study about the Maxwell's law of distribution of velocities and its derivation. So let us start with this term. What is meant by the Maxwell's law of distribution of velocities? So let me write down Maxwell's law of distribution of velocities. We know that the gas molecules have fixed mean kinetic energy at a particular temperature. But this does not mean that the molecule is moving with the same speed throughout its motion or movement. After each collision, so this will be one of the collision and there is another collision. So after each collision, the speed of the molecule changes, and due to a large number of collision, speed is different at different times. But the root mean square velocity C RMS remains same at a fixed temperature. So this CRMS, it depends on the temperature and it is found to remain constant at a given temperature. At any instant of time, all the molecules are not moving with the same velocity. Some are moving with higher velocities than the root mean square velocity, and some are moving with lower velocities than the root mean square velocity. But the mean kinetic energy of the molecule remains constant at a given temperature. Now this Maxwell and Boltzmann equation, this is called as a Maxwell's Boltzmann equation. It forms the basis of the kinetic theory of gases. This equation, it defines the distribution of speed of for a gas at a certain temperature. So how is the distribution of the speeds? In what way we will assign speed to the molecule? From the distribution function, the most probable speed and the average speed and the RMS speed can be derived. So this is the equation that gives us the values of this most probable speed, the average speed and the RMS speed. Now this Maxwell-Boltzmann distribution, it is used to determine how many molecules are moving between the velocities c and c plus dc. So if you take a range from c to c plus dc, then this Maxwell-Boltzmann equation, this can be used to determine how many molecules are moving between this velocity range. Okay, so let us see some of the terms which are involved in this equation and how we can derive this equation. So let us see the derivation of the Maxwell's equation. For this, we will make certain assumptions. Now the first assumption that we are going to make is that due to a large number of molecules, the number of molecules in any region is same and it possesses same velocity in all directions. So we have large number of molecules. It is the assumption of kinetic theory of gases. And because of this large number of molecules, the number of molecules in any region is same. And if you take a small region like this, then the number of molecules in this region, if you take a region on this side or on this side, the number of molecules will be same in any of the region, and it possesses same velocity in all the directions. So same region and same velocity. So same velocity in all directions. So this is our first assumption. Now the second assumption that we are going to take is that the velocity components along the three perpendicular axes, mutually perpendicular axes that we have considered here. This is your x, y, and z axis. So if you take the three perpendicular axis, mutually perpendicular axis, the velocity component along these three perpendicular axes, they are independent of each other. So these velocity components are independent of each other. And the third assumption that we'll be considering is that randomly selected molecules has certain velocity limit and it is related to the probability. So if you randomly select any number of molecules, then this will have certain limit and that is related to the probability, and this probability is a function of the velocity. So these are the three assumptions that we are considering, and here we have taken this OX, OY, and OZ as the three mutually perpendicular axes. Then we'll take C bar as the velocity, and this C bar velocity is having components u, v, and w along the three axes x, y, and z. So u, v, and w. So we can take this as y and this as z. So that you can write this c square as equal to u square plus v square plus w square. Now if you take a point P here, this is called as the velocity point, and therefore you can write down this f of u du. This will represent the probability that the molecule which is selected at random has a velocity between u and u plus du. So this function f of u du, it is representing the probability that the molecule selected at random will have velocity between the range u and u plus du. In the same way, you can select f of v dv, which will represent the probability that the molecule which is selected randomly has velocity between the range v and v plus dv. Similarly, you can take for the third one, that is f of w dw. This is also representing the probability for the molecule to be having velocity in the range w and w plus dw. Now let us consider a small volume element in this velocity space, and this volume element will be given by du, dv, dw between, and in this velocity element, the molecules having component velocities between the range u and u plus du, v and v plus dv, and w and w plus dw. Now let us take n as the total number of molecules. We'll take dn as the probable number of molecules of the velocities in the x direction between u and u plus du, and we'll take dn by n as the fraction of molecules of velocities. So this is the fraction of molecules of the velocities between this u and u plus du, or this can be the probability of finding the molecules between the two planes. So let us write down what is the RMS velocity of this molecules that we have considered. So the mean square velocity of the molecule is given by c square is equal to 1 upon n integration from 0 to infinity this c square dn, where we have taken this dn as the number of molecules having velocity between because we are writing this c, this will be between c and c plus dc. So we have taken n as the total number of molecules, and the component of velocities in the x direction is from u to u plus du. Now the fraction dn by n, if we write this in terms of x, then this dnx upon n, this fraction is a function of u. It is a function of the velocity u only, and this is proportional to du, so that you can write this dnx upon n as equal to f of u du, because just now we have defined what is f of u du. So therefore we can write this dnx as equal to n f of u du. Similarly, for y and z direction, you can write this dny as equal to n f of v dv and dnz as equal to n f of w dw. So we have now written the fraction of molecules moving along the x, y and z directions. Now this value n is very large and du is very small as compared to u, and there are large number of molecules in the range u and u plus du. Therefore the fraction dnx of the molecule whose y component of velocities range between v and v plus dv will be given by the equation this d2nxy upon dnx, which can be written as dny upon n, and this is equal to f of v dv. So that you can write this d2nxy as equal to n f of u f of v du dv. Now this number d2nxy is also very large, therefore we can consider the fraction dnxyz. Now what we are considering? The fraction dnxyz molecules whose z component of velocities range between w and w plus dw. So this will be given by the equation d2nxyz as equal to n f of u, f of v and f of w. This will be du, dv and dw. So let us now write this in this form, like this is suppose a function u, the rho, sorry. So this function will be written as d2nxyz upon this du, dv, dw. This will be equal to, now this is n f of u, f of v and f of w. So if you take this as equation number 1, now we know that there are no preferred direction of velocities, and this term, which is representing the density of velocity points, this will be constant. So this is nothing but the density of velocity points, and therefore this term will be constant. Now if this is constant, it means that you can write this function n f of u, f of v, f of w as equal to constant. So that you can write this n f of u, f of v, f of w as equal to constant. So let us take this as equation number 2. Also, we have c square as equal to u square plus v square plus w square. This will also be constant. And let us take this as equation number 3. Now our work is to find out the differentiation of equation this 2 and equation 3. So we'll find its differentiation, and after partial differentiation, what do we get? So this is the product, and we have to apply the product tool here, and will be constant only. So we will have to apply product tool for this function 1, 2 and 3. So when you apply the product rule for these functions, you know that the first function, if it is kept constant, if you differentiate this first function, then this two will be kept constant. Then the second time we will differentiate this, and this two will be kept constant. And third time we'll differentiate this, and the first two will be kept constant. So applying the differentiation rule, we will get this as, so we are differentiating the first function del f of u upon del u into this du. So we'll keep the other two constant, f of v, f of w, plus now we have the second differentiation, so del f of v upon del v into this dv, and the other two will be kept constant, that is f of w and f of u. Then we have the third one, so the last one will be differentiated partially, so del f of w upon del w into this dw, plus so into, you have the first two, that is f of u and f of v here, and this will be equal to 0, that is the differentiation of the constant. So let us take this as equation number 4. In the same way, when you differentiate equation number 3, we get this as twice u du plus twice v dv plus twice w dw as equal to 0, or you can write this as u du plus v dv plus w dw as equal to 0. So this is equation number 5. Now we are going to simplify these equations 4 and 5. So when you simplify these equations 4 and 5, what do you get? So this equation will divide equation 4 by f of u, f of v, f of w, so that we get this term as 1 upon f of u del f of u upon del u into du plus 1 upon f of v del f of v upon del v into dv plus 1 upon f of w del f of w upon del w into dw. So this will be what we have done. We have divided by this term f of u, f of v, f of w. So therefore we'll name this equation as 6, and then we have this equation 4, 5 and 6. Now suppose this dv and dw are arbitrary values, then this equation 6 can be multiplied, this equation 6 can be multiplied by one multiplier which is called as a Lagrange's multiplier, and this is m into beta. We will take this m as the mass of the molecule and beta is some unknown arbitrary function. So we will multiply this equation 5, the equation 5 by this m beta. So multiplying equation 5 by this m beta. When you multiply this by m beta, so when you multiply it by m beta, we will get the equation as m beta into u du plus v dv plus w dw, that is equal to 0. So this is equation number 7. Now adding this equation, we'll add this with the equation, let us see which was this equation 6 and 7. So when you add equation 6 and 7, what do you get? So after adding this equation 6 and 7, you have here m beta u du. So we'll add the du terms, bring the du terms together, dv terms together and dw terms together. So after adding, what do you get is this one. This is 1 upon f of u del f of u upon del u, plus here you have m beta u. So this is m beta u into this du, plus you have the second term 1 upon f of v del f of v upon del v plus m beta v into this dv, this is dv here, plus 1 upon f of w del f of w upon del w, and here this is m beta w into this dw, this is equal to 0. This will be your equation number 8. Now this v and w are considered to be independent and their differentials are arbitrary. So therefore we can assign 0 for this dv and dw. So assigning, if you put this dv is equal to 0 and dw is equal to 0, then this equation will become 1 upon f of u del f of u upon del u plus m beta u is equal to 0. We are taking du as equal to 0 and dv as equal to 0, dw as equal to 0 and du not equal to 0. If du is not equal to 0, the term, this bracket will be equal to 0. So similarly we get 1 upon f of v del f of v upon del v plus m beta v as equal to 0 and 1 upon f of w del f of w upon del w plus m beta w as equal to 0. So you can, if you want, again give numbers to this. This will be your equation number 9, this is equation number 10 and this is your equation number 11. Now if you want that the equations, the above equations that we have taken 9, 10 and 11, if suppose these are to be satisfied, then beta must be either constant or it should be a function of the variable in the equation, and the function f, it satisfies the same differential equation irrespective of any component. Now for the x component, we can write this. You have here the first equation, 1 upon f of u del f of u upon del u plus m beta u is equal to 0. So this can be written This can be written as d du of log of f of u as equal to minus m beta u. So we have taken this term 1 upon f of u del f of u upon del u. This has been written in this form d du of log of f of u, and the other term is transferred on the right hand side. Now if you take integration of this term, so we get integration of d of log of f of u as equal to minus m beta integration u du. After integration, we get this term as log f of u as equal to, now here we have minus this beta, and integration of u will be u square by 2, so you can write this as m u square by 2 plus some constant of integration, that is log a. Now this a is the constant of integration, and from this equation you can write this f of u as equal to this constant a into e raised to power minus beta into this half m u square. Similarly, we can write this f of v as equal to constant a into e raised to power minus beta into half m v square, and f of w as equal to a e raised to power minus beta into half m w square. From these three equations, the density of velocity point that we have written earlier can be written as, so we can write the density of velocity point, which was represented by rho, density of velocity point, which was rho. This will be equal to, it was n f of u, f of v, f of w. So we are multiplying the three terms. This will be n, and it is a cube. If you multiply by other all the three terms, then this is e raised to power minus beta into, this is half m into u square plus v square plus w square. So therefore this rho can be written as equal to n, and this is a cube e raised to power minus beta into half m c square, because we have taken c square as equal to u square plus v square plus w square. Now this rho is constant within the volume space that we have considered with radii c and c plus dc. Now the volume of this element is 4 pi c square dc. So we know that this rho is constant. If you take the shell to be, if you take this as a small spherical shell with radii c and c plus dc, then the volume of this element will be equal to 4 pi c square dc. Now this volume element contains dn number of molecules, and therefore this rho can be written as equal to dn divided by 4 pi c square dc. Now here we have rho is equal to na cube e raised to power minus beta into this term, and here we have rho is equal to dn upon 4 pi c square dc, and therefore equating the two terms we get this dn upon 4 pi c square dc as equal to na cube e raised to power minus beta into half m c square. So thus we can write dn as equal to, or you can write dn upon dc as equal to, we have to transfer this 4 pi c square on the right hand side, and therefore you get this dn upon dc as equal to 4 pi c square, you have your n then we have a cube e raised to power minus beta into half mc square. You can write dn as equal to 4 pi n, then we'll write this a cube e raised to power, this is a minus bc square, and here we have c square, this one dc. So let us take this b as equal to, so what we have substituted here is we are taking b as equal to beta m by 2 or half m beta by 2, and let us take some constant a which is equal to under root of b by pi, and we know that beta is equal to 1 upon kt. So therefore you'll get this a as equal to under root of, if you take b as equal to beta m upon 2 and beta as equal to 1 upon kt, so you'll get this as m upon twice pi kt. K is the Boltzmann constant. Now therefore we can write this function dn upon n or dn upon dc as equal to, therefore you can write this dn upon dc as equal to 4 pi n, this will be a cube, so it is m upon twice pi kt raised to power 3 by 2 into e raised to power minus m c square upon twice kt into this c square. So this is the equation that is called as the Maxwell's law of distribution of velocities, and this equation can be plotted into a curve that represents that gives us the distribution of velocities. So let us see how the curve is. So let us see the curve. So when you plot this curve, you'll get a curve of this type. Now this is called as the Maxwell law of distribution of velocities curve. The number of molecules possessing the root mean square velocity Vrms, it is maximum. The number of molecules having very low or very high velocities, it is small. The shaded region, it represents the number of molecules dn having velocities between c and c plus dc, and the total area under the curve, it represents the total number of molecules. So in this way we have completed the section for the distribution of velocities, and from this we can find out what is the average speed, and the average speed is the sum of the speeds of all the particles divided by the total number of particles. Then the most probable speed is the speed associated with the highest point in the Maxwellian distribution. We have already seen how these are related, and we have also seen the formulae for CRMS and in our earlier lectures. So that's all for now.